Hey everybody, let's take a look at what this double vertical bar means before we dive into this problem. 2 squared divides single vertical bar 104 since 104 is equal to 4 times 26. All right, now that's clear, right? That's what we mean by divides. 4 times 26. A number is a divisor of another integer if there's another integer such that the product of said number is that integer. Okay, so this is an example of the single vertical bar, but this double vertical bar means divides exactly. And let me write down an example of that. 2 cubed divides 104 exactly. So what we do is we put a double vertical bar. What that means is that no higher power of 2 divides 104. Note that 104 is equal to 8 times 13, right? So there's not any higher powers of 2 that do this. Okay, so again, 8 is the same as 2 cubed, right? So that's the meaning. This double vertical bar, Charles Vanden Eynden called that divides exactly. Other authors have called it divides fully. You know, there's argument about which particular term to use, but it has a very specific meaning mathematically. Now, notice, just to be sure before we move along, 2 squared does not, and I'll put the slash for the negated relation here, 2 squared does not divide 104 fully, right? Because there's another power of 2, as we've seen, that you need to get that effected. Okay, so anyway, that's the meaning of the double vertical bar. So we're supposed to produce a natural number or positive integer n such that this statement is true. Now let's rewrite this. These things are kind of rigged to work out nicely. 2048 is equal to 2 to the 11th power. Computer scientists are quite familiar with that. It's just binary. All right. Now, let's keep going here. Notice that if you think of this factorization here as a squared minus b squared, and again, your a would be 3 raised to 2 to the 10th power, and your b would be 1, okay? Notice that this piece right down here would be a plus b, and the piece following it would be a minus b. Okay, so this would be a minus b right here. All right, and it's a little sneaky rules here, but notice that, remember what you do when you're multiplying exponential quantities like this is you add the exponents. So what we really have here is 2 to the 9th, 3 to the 2 to the 9th, or well, we'll just say it like this, 2 to the 9th plus 2 to the 9th, and the idea will be conveyed this way. 2 to the 9th plus 2 to the 9th is the same thing as 2 times 2 to the 9th. Okay, but remember, what does that mean? That means you have 9 copies of 2 and 1 copy of 2, which is 10 copies of 2. So that's why you add your exponents. All right, so that gives you 2 to the 10th. See, and that kind of thing is happening exactly in this step right here. Notice how this 2 to the 10th is the product of 3 times 2 to the 9th times 3 times 2 to the 9th. All right, and this process repeats. Okay, I won't do the rest of it, but you can see what happens here. The 3 to the 2 to the 9th plus 1 made it to this stage, and then we did the very same thing with 3 to the 2 to the 9th minus 1. That was done as the difference of 2 squares, and I won't detail that because it'll clutter things up. But you can see this will go on for as many stages is this value 10, okay? And so this very next line, you can just see how this continues and continues. 2 to the 10th, 2 to the 9th, 2 to the 8th, ellipsis 2 to the first power. Now right here, just to be clear, this technically would be 3 raised to the 2 to the 0 power, but 2 to the 0 is 1, and 3 to the 1 is, of course, 3. All right, and right here, this is, again, 3 times 2 to the 0. And so you see this pattern carries on for however many steps here, and we're about to figure that out. Okay, so our original problem is actually equal to this factored product. Now there's a result. There's a result that I proved in the last video that says 2 perfectly divides or exactly divides something in this form 3. What do you want to? We can use the variable n if you want to. 3 times 2 raised to the n power plus 1. Now that requires a little bit of work to actually prove this, okay? But it is true, and you can check this out, folks. If you check this out, like for example, with n equals 1, you would get 3 squared plus 1, which is 10, and 2 divides 10 exactly, since 10 is just 2 times 5, okay? Now in a similar fashion, I think if n is 2, you would get 3 to the 4th, which is 81, plus 1, which is 82, and 2 divided by 82 is 41. So 2 times 41, and again, 2 divides this expression fully or exactly, all right? So you see, this is going to happen 10 times starting right here, all the way from 10 to 1 right here, all right? So you see, that means that you have 10 factors of 2, and I'll write that down, 10 divisors of 2, if you want to say. 10 divisors of 2, right? And y'all, that's happening exactly from here to here. Here's 10, 9, 8, all the way to 1, okay? So that's 10 divisors of 2 in each of these parenthetical quantities. All right, and then right here, there would be 2 divisors of 2, right? There would be, since 4 is equal to 2 times 2, you get 2 more, and finally there's another factor of 2 right here, right? So we have 10 plus 2 plus 1, okay, equals 13, and that is the n we're looking for, okay? In other words, back up here, we're looking for an n such that this is true, and so the n is equal to 13, and that's the final answer. Pretty sure I did it right, although these numbers are so ginormous that you would never know. You just have to trust. I guess there's big number calculators out there, but n equals 13 is the solution, at least the way I calculated it. And so everything was done in a straightforward fashion, other than this result right here. This is something that has to be proven. I certainly did not prove it right here, but you can prove this with the binomial theorem or even just modular arithmetic, I think. 2 divides this expression fully or exactly for n. Let's see, it works for 0 too, right? Because you would just have just 4 right here, right? Or 3 to the 1 is a 1. So yeah, it works for n equals 0. Any non-negative integer. And yeah, the proof of this was done in the previous video. So, but anyway, that is the fact we had to appeal to. This fact gave us these 10 divisors because these expressions right here all the way across are in this form, okay? All right, folks, that is it. Hope you enjoyed the video. I liked it quite a bit. Pretty reasonable. It's considered to be an IMO preparatory problem way back in 2006, I think.